we are picking up with our recorded lecture. This is Chapter 2, beginning Part 4. So we're going to do some more sample problems related to acceleration. In this one, we're told we have the tip of a robot arm is moving to the right at 8 meters per second. So we know our velocity is 8 meters per second, and because it's moving to the right, we're going to put a plus. 4 seconds later, it is moving to the left, so we're going to put a negative at 2 meters per second. So we know our 8 meters per second is initial, our negative 2 meters per second is final, and the time is 4 seconds. You're asked to find the change in velocity, and you're asked to find what the acceleration is. Well, we know that the change in velocity is the final velocity minus the initial velocity. So our final is a positive 8 meters per second, and our initial velocity, oops, I got that backwards. Okay, so our final velocity is a negative 2 meters per second, and our initial is subtracting a positive of 8 meters per second. So our delta V is going to be negative 10 meters per second. And our acceleration is delta V over delta T. Well, we just calculated what delta V is, which is negative 10 meters per second. Our acceleration is 4 seconds. So that gives us an acceleration of negative 2.5 meters per second squared. Okay, in our next problem, we have an arrow that accelerates from 0 to 40 meters per second. So we know that our initial velocity is 0 meters per second. Our final velocity is 40 meters per second. And our time is 0.5 seconds. And you're asked for the average acceleration. So we know average acceleration is delta V over delta T. So our average acceleration is going to be our 40 meters per second minus 0 divided by 0.5 seconds, which will give you 80 meters per second squared. Okay, let's do another one. So in this one, we had a jetliner traveling northward is landing with a speed of 69 meters per second. Once the jet touches down, it has 750 miles of runway in which to reduce its speed to 6.1 meters per second. You're asked to compute the average acceleration, magnitude, and direction of the plane during the landing. Notice, assume constant acceleration. So that tells you you're going to be using one of the kinematic equations. So let's make our list of what we're given. So we know our initial velocity in the x direction is 69 meters per second. We know our position is 750 meters. We know our final velocity in the x direction is 6.1 meters per second. So since we're given velocity and position, and we're looking for acceleration, we're going to use the third kinematic equation. And that third kinematic equation is the final velocity squared equals your initial velocity squared plus 2 times the acceleration times delta x. And we're looking for acceleration, so we need to do some rearranging. So the first thing we're going to want to do is go ahead and move over our Vx initial squared. So we're going to subtract on our right Vx initial squared, and we're going to subtract it also on our left. So that's going to cancel on the right. So we have Vx final squared minus Vx initial squared equals 2ax delta x. And now we're going to divide both sides by 2 delta x. So on our right, we're going to be canceling the 2's. We're going to be canceling the delta x's. So we're going to be left with our acceleration in the x direction is x final squared minus the velocity initial squared divided by 2 delta x. So we're going to have our 6.1 meters per second, that will be squared, minus 69 meters per second, that will be squared, divided by 2 times 750 meters. And that is going to equal your acceleration in the x direction. And I'm kind of running out of space. The acceleration will equal negative 3.1 meters per second squared. So this is your answer. Acceleration is negative 3.1 meters per second squared. Okay, let's try another one. So in this one, we have a bullet going 310 meters per second, strikes a 5 centimeter thick target, and you're asked 2 things. A, the constant acceleration required if the bullet's to stop within the target, and B, the acceleration if the bullet emerges from the target. Okay, so let's make our list. We have our initial velocity equals 310 meters per second. And we have delta x equaling 5 centimeters. Well, we know that has to be converted to meters, so do it right now so you won't forget it. So in 1 meter, we have 100 centimeters, which is going to give us 0.05 meters. Okay, and then for part A, our final velocity is 0. And for part B, our final velocity is 50 meters per second. So again, we're going to use that third kinematic equation, which we just rearranged for in the previous problem. So your third kinematic equation, when we rearrange it, we have AX equals VX final squared minus VX initial squared over 2 delta x. So that's the equation we're going to use for part A as well as part B. So in part A, we're going to have AX equals 0 minus 310 meters per second squared, and that's all squared, divided by 2 times 0.05 meters. So that will give you a negative 9.6 times 10 to the 5th meters per second squared for the acceleration. And in part B, your acceleration is now going to be 50 meters per second. That is your final velocity when the bullet emerges from the target at 50 meters per second, minus 310 meters per second squared. And I just noticed that I put a square right here, and that should not have been. That is just meters per second. Okay, and then we're dividing that by 2 times 0.05 meters. And so for part B, you get an acceleration equals to negative 9.4 times 10 to the 5th meters per second squared. So this would be your answer for part A, and this is the answer for part B. Now we also want to talk about free fall. And so free fall is particularly important example of constant acceleration. And it is the motion of an object moving under the influence of gravity only, no other forces. So because it's only under the influence of gravity, we call it free fall. Strictly speaking, free fall only occurs in a vacuum where there's no air resistance. So Galileo discovered two objects in free fall, regardless of their mass, have the same acceleration. So our common example is to drop two objects. Prime example is a coin and a feather. And you're dropping them inside a plastic tube where all the air has been removed. So you have a vacuum. In that vacuum, they're both going to fall at the same rate. Astronauts conducted that same experiment on the moon because there's no atmosphere on the moon. So on the moon, they dropped a hammer and a feather, and they fell at the same rate. So when we look at free fall in terms of a motion diagram, we see that for an object dropped from rest, your velocity vector is pointing down, that's your green one, and the orange is your acceleration, it's also pointing down. Now notice how your velocity vectors get longer as they go down. So if you graph it, notice you come up with a negative slope. So therefore you have a negative acceleration. So when you're looking at the motion diagram, remember constant acceleration means that the speed changes by the same amount during each second. So if we can find the ball's speed changed by a certain amount of time during 1 second at the beginning of flight, it would change by the same amount during any other 1 second of flight. Now, free fall, your acceleration always points down, regardless of whether your object is being thrown up. So in this case, your object is initially going up. Notice how your velocity vectors are getting smaller because the object is approaching a stop. But your acceleration vector is always pointing down. So free fall acceleration is always in the same direction. And on Earth, it has approximately the same magnitude. So the acceleration of free fall equals g, which is 9.8 meters per second squared. That's a constant. A lot of times we'll round it to 10 meters per second squared. If you're in the English system, it's 32 feet per second squared, vertically downward. For the most case, when you're doing math problems, you're going to keep it at 9.8 meters per second squared, unless in the problem I tell you to use 10. Now, by definition, g is always positive. But when we look at one-dimensional acceleration, ay equals a of free fall, and that equals negative g. So it's the ay that's negative, not g. G's not called gravity, it's free fall acceleration. Okay, let's look at this problem. So in this one, you're asked to find the velocity of an egg that's dropped off a media center as it impacts the ground if the media center's roof is 15 meters tall. Find the velocity of the egg if it's thrown downward at 10 meters per second. Assume constant acceleration. So that tells us that we're dealing with a kinematic equation again. So we're going to use our third kinematic equation. So third kinematic. And that third is, now we're in the y direction. So we're going to change it to Vy final squared equals Vy initial squared plus 2ay times delta y. And if you wanted to draw a little picture, here's our ball, here's our set. So this distance would be your 15 meters. So we know that ay equals negative 9.8 meters per second squared. Okay. Delta y is going to equal y final minus y initial. Okay, well, finally, it lands on the ground. So our final is 0. We're starting out with 15 meters. So delta y is going to be negative 15 meters. Our initial velocity, so Vy initial, the ball's just sitting there, so it's 0. And you're asked to find the final. Okay, so so this is, we're going to start, we actually have two parts. We have part A and a part B. So let's do the first part. So we want to find Vy final. So we know that Vy final squared is going to equal Vy initial, which is going to be 0, plus 2 times negative 9.8 meters per second squared times negative 15 meters. So we have Vy final squared equaling 294 meters squared per second squared. Now I only want Vy, so Vy is going to equal the square root of 294 meters squared per second squared, which is going to be 17 meters per second, and it's going down. Okay, now in part B, we're using the same third kinematic equation. We're also looking for Vy final, but now we're throwing it downward at 10 meters per second. So for part B, our initial velocity is now going to be negative 10 meters per second. So then when we look at what Vy final squared is going to be Vy initial squared, which is minus 10 meters per second, that's all squared, plus 2, well, let's put the 2 inside. Plus, we have 2 times negative 9.8 meters per second squared times negative 15 meters. So Vy final squared will equal 394 meters squared per second squared. And then we take the square root of Vy final. So that's going to give Vy final will equal negative 19.8 meters per second. And the negative sign does indicate it's down. Then our last problem we want to look at in chapter 2. See, if a ball is traveling downward at 40 meters per second with a constant acceleration of 10 meters per second, what will be the ball's speed 1 second later? If the same ball is thrown upward, what would be the speed 1 second later? So let's do the first part. Our ball is traveling downward, okay? And in this case, we want to use our first kinematic equation. So our first kinematic equation is Vf equals Vi plus At. So we have our our Vi to be 40 meters per second. Our acceleration is 10 meters per second squared, and our time is 1 second. So we have Vf equals 40 meters per second plus 10 meters per second squared times 1 second, and that's going to give us a Vf of 50 meters per second. And now for our part B, where we're throwing the ball upward, our Vi is still 40 meters per second, but our acceleration is a negative 10 meters per second squared, and our time is 1 second. So Vf final is going to be 40 meters per second plus negative 10 meters per second squared times 1 second. So Vf is going to be 30 meters per second. Okay, this ends chapter 2 recording.